Okay, so the final presentation is an attempt anyway to inject a bit of science, I guess. So I'm going to try and do this. For a start, it's not, as I've already explained, I'm a turbine engineer, so I'm doing this on behalf of Damian Hampshire, who heads up the nuclear fusion work at Durham. And I'm not an expert, it's probably advantageous in this situation, so I'll try and get the messages across in a technical but accessible. So the title of this final presentation in our slot then is the European Fusion Energy Reference Laboratory for Superconducting Materials in Durham. So we've got superconducting in there and reference laboratory, neither of which are immediately apparent how that wraps on to nuclear fusion. So hopefully I'll be able to explain that now. So essentially, why isn't Damian here? Well, there's actually quite an important meeting going on in this field in the UK at the moment, and so he's a keynote speaker at that meeting over in Cambridge, which is why I agreed to do this presentation today. So what we're going to do in this presentation is very quickly really start off talking about superconductors, look at applications of superconductors, say a little bit about what they are, and then get into the main meat of the presentation, which is to talk about ITER, the International Thermonuclear Experimental Reactor. That is the major global project underway at the moment, looking at trying to make nuclear fusion a reality. And then say a little bit at the end about the measurements and calibrations facilities in Durham. Okay, so applications of superconductors, there they are. I think probably most people have heard of superconductors, come across them in various spheres so far. What is a superconductor? Essentially, it's a conductor with zero resistance, which sounds great. You know, if you have zero resistance, then you can transmit power from one place to another with essentially no loss. So that sounds fantastic. The trouble in order to create a superconductor is it has to be very cold. Okay, so you have to cool the materials down to temperatures of around 10 Kelvin. So only 10 degrees above absolute freezing. So they're relatively easy temperatures to achieve in the laboratory environment. That's not too difficult these days. And indeed, in specialised pieces of equipment, such as MRI scanners, again, the laboratory technology can relatively easily be rolled out commercially in those sort of devices. So you do find superconductors being used in medical devices and in some of these other technologies there that are highlighted in red in the slide. The red ones have not yet been realised, so it would be nice we talked a lot about cutting down on transmission systems, removing overhead power lines. Another side of the coin might be if you could make the power lines out of superconductors, the losses would be a lot less, you'd need far fewer of them, so it will be another way of reducing that infrastructure. The reality is though, even though it would be great if you could do that, at the moment the temperatures that you require of these devices in order to get them to operate are so low that it's just not, it is a long way off being feasible to be able to transmit power over any appreciable distance with technologies in stand at the moment. And finally, the one that we're going to talk about in most of this presentation is ITER, the use of superconductors in achieving nuclear fusion. And that's a much more closer reality than power transmission, as hopefully you'll be convinced in a few moments. So basically, what is ITER, or it's sometimes called tokamak as well, as you see at the top of the slide there, means the same thing. Well, essentially, the heart of ITER, the heart of the International Thermonuclear Experimental Reactor, is nothing more than a transformer, which is what you see there. So you have a central solenoidal magnet, an electromagnet there. You put a current, a voltage across high current, high voltage through that central core, if you like, and that induces very large currents into the electromagnets that surround it there, and those currents, or the energy from those, goes to produce a plasma within the toroid, as you see the picture there. And the temperature of that plasma it says 100 million degrees there. I'm looking at the particle physicist in front of me. I'm sure, as I'm not an expert, I'm sure that's right, seems very high to me. And it also instantly brings to my mind as an engineer how ridiculous the temperature scale is, if you think about it. Because we're all happy to live in a world where we're now 20 degrees C in this room, and we all accept that you can go to minus 273 degrees. So if this, if this is where we are in the room, then minus 273 might be here, and you can go as many million as you like in that direction, and we all live in this little area. It's all very highly non-linear. So the numbers, when you actually think about them, bizarre things go on in the way we measure temperature. Anyway, the plasma is hundreds of millions of degrees C, but you have to get the superconductors that sit within the coils that you see there. They have to be operating at very low temperatures in order to achieve these sort of devices. So that is what ITER will look like. So to give you an idea of scale, if you look very hard, you can just see a human being standing in this, just in this bottom corner here. I don't know if you can see it in the back there. Anyway, he's that whole device there is maybe 20 human beings high, 24 meters across. You can see that's in the dimension. Like engineering now, we've got a dimension on there. So this is a huge machine in order to, in terms of scale, in order to do this hopefully achieve this first demonstration of nuclear fusion generating power. The numbers on the left-hand side there, if you look halfway down, you've got electrical energy input 20 megawatts. So that's the amount of power that you need to excite the central core of the transformer, if you like. And the fusion power, the energy it releases into the plasma going around the donors, if you like, in the middle there, is 500 megawatts. So you have a power increase of 20 megawatts in, 500 megawatts out. And you can only achieve that if you're using superconductor material in order to form the electromagnetic coils. If you have ordinary materials in their ordinary conductors, then you wouldn't need 20 megawatts of power in. You would need far much more power going into the device than you would get out in order to form the plasma. So it really is the superconductor element of the device, if you like, makes it all possible. If it wasn't for that, it wouldn't be able to achieve the conditions in the plasma that you need. So once you've generated the plasma, it's within the plasma then that you can get the nuclear fusion reaction to happen and the energy, or this huge amount of energy to be released. Unfortunately, though, we still can't do away with heat engines. Somebody was talking about heat engines earlier on and how moving to renewable or different forms of energy. One of the advantages of that is heat engines may become a thing of the past, or not if you adopt this technology. How do you get the power out of it? Well, this plasma that you create with this nuclear fusion reaction going on, you have to cool the plasma itself. I don't actually know what gas that it's intended to use for ITER. I would imagine it's carbon dioxide. You do? Any ideas? Carbon dioxide, I would have thought. There's lots of current nuclear reactors around, advanced gas cooled reactors using carbon dioxide. So you use carbon dioxide to take the heat away from the plasma, and then that will go through a secondary steam generator. It'll be used to raise steam, and the steam will be expanded through a conventional steam turbine generating set to produce power. So even with these advanced reactors, you still need a good old heat engine, and the first and second laws of thermodynamics are our old friend in order to generate usable power from. Cost of it, to use a cool $15 billion gets you this demonstration. It's a little disappointing that the indicative burn time there is only 500 seconds, that's just under 10 minutes, but I think I did ask David why or what happened if you went when you got to 501 seconds, and the answer is he didn't actually know, but he said that's just the specification of what we're trying to achieve in the first instance, but this technology is clearly designed, or if it's going to be any use at all, it will need to be designed and deliver like a conventional nuclear power plant does, and capable of pretty much base load 24/7 operation. Okay, why move to it? Well, fuel's essentially limitless, so deuterium from seawater and tritium from lithium. I think no greenhouse gases. I thought that was a bold statement. Major nuclear accidents impossible. I think if in any way the reactor is breached, then it stops, basically. So there's no chance of any large-scale nuclear releases of the type that you have with conventional reactors. No longer radioactive waste to worry about. But as I say, it really requires this world-class superconductor technology, and the superconductors themselves are about a third of the cost of the whole project in order to deliver that technology. And it's expected that it'll first run 9 years from now in 2024, as you see there. So that is a more detailed view of the heart of the matter. And what's Durham's contribution to this? Well, we're not. Very clearly, this is a global effort. So Durham's expertise is not in nuclear fusion at all, really. It's in the superconductor materials, and in particular in the measurement of their performance. So that's why, at the top of the slide, it said that the lab was a reference laboratory. So what the researchers at Durham have a particular expertise in is developing methods and techniques for really measuring and confirming the performance of the superconducting materials, and they also have research interests in developing new superconducting materials. Ideally, or the principal focus is basically getting the superconduction to happen at higher temperatures than is possible at the moment. So those are the two big research threads, if you like, to the activity at Durham. At the moment, the toroidal field coils, which are the ones in, I keep pointing at the screen here, which you can't see, of course, the ones in gold there. So Durham has the element of the or is contracted to ITER to basically measure and validate and confirm the condition of all of those coils for ITER, so all the toroidal coils. And for the polyoidal coils, which are the ones that go around the outside of the reactor here, some of those are made in Europe, some of those are made elsewhere. The ones that are made in Europe, again, Durham has the contract to do the testing of those and the confirmation that they are fit for purpose. So the toroidal coils themselves, they're made out of this niobium tin compound. The superconductors themselves are just under 1 millimetre diameter wires. There's 1,100 of them twisted together to form each coil. 820 metres, almost a kilometre long in total, wound round to form each one of these toroidal coils that go around the core of the device. And similarly for the polyoidal field coils, they're made out of a different material. Again, niobium, but this time a niobium 10, niobium titanium material. Again, those will be tested, or the European ones will be tested at Durham. This material, you have to get it down to temperatures of below 9 Kelvin in order to get it to superconduct properly. The niobium material used for the toroidal coils is a little less demanding. You need to be below 18 Kelvin for those to superconduct. That's what they look like if you look at cross sections of them. So these two pictures on the left-hand side there show the niobium tin superconductors using toroidal coils. There's two manufacturers of those, so they have two slightly different forms, and then the other superconductors, the niobium titanium ones, look very different in their format or in their making. And essentially, these are the sort of facilities that we have at Durham. So what you're looking at here are vessels that we're able to pull down to very low temperatures. So this one on the right-hand side here, the silver thing on the top right-hand side of it, that's a cryogenic cooler. So that small off-the-shelf device there, you see those sitting on top of medical machines as well. That's £10,000 worth of equipment. It's able to pull the temperatures down within that vessel to temperatures certainly below 5 Kelvin. And then the samples of superconductor material are put into those vessels. They're exposed to very large magnetic fields. The currents that are induced within them are measured. And that's how the materials are validated and quantified. So that's a typical sort of result that you get. So looking at we've got a graph up there at last. So I'm in happy land now. So we've got on the horizontal axis there is the current going through the superconductor, and then if we just concentrate on the left-hand side, that's the voltage across the superconductor. So anywhere where that voltage is zero, essentially there's no resistance of the conductor there. So in this particular test here, which was carried out at a temperature of 4.2 Kelvin, you could get over more than 160 amps going through the superconductor, all with essentially zero resistance, no loss, and it wasn't until you go above 160 amps that you sort of fall off the cliff face, and you suddenly start needing voltages and resistance starts to happen. So that temperature there, 160, in that case, is known as the critical current for that device. And unfortunately, the critical current that the device can take depends upon the strain on the material as well. So as you're operating these superconductors, things get very hot, and the filaments themselves come under strain, and that affects their performance. So Durham have devised techniques as well for exposing the superconductors to strain and measuring their performance under different degrees of strain. A very busy graph, but essentially looking very quickly at this figure on the right-hand side here. So you have the amount of strain on the bottom here. So zero, sort of up here is no strain, and then when you move either side of zero, you're either in compression or in tension. And what you really want is the critical current, which is critical currents on this side of the graph here. You want that to be as high as possible, so you can see from these graphs they're all different colours, correspond to different temperatures. But in actual fact, when you put them under a little bit of, I think it's compression, under a little bit of tension, things actually get a bit better if you look there very closely before the form starts to drop off a bit. But again, the materials are designed such that you can put strains on them up to a certain level without doing too much damage in terms of the critical current that they can withstand. So this sort of data is what Durham produces, and that's used then to convince the project, if you like, that the coils either are good or not fit for service. And quite a lot of them have been rejected as a result of tests done at Durham, and the quality of the operation. You can imagine there's big money involved here. So manufacturers of the superconductor materials challenge those results quite aggressively on occasions, but I'm pleased to report that the Durham data has always come through with flying colours and being upheld. Okay, so there's a couple, I think I'm more or less out of time, there's a couple more slides here. These are really just showing other facilities at Durham. Helium is the cooling material used for the superconductors themselves. A lot of it is used in testing as well. Helium's it's expensive, and there's a bit of a world shortage of it. So a focus of the Durham research work has been looking at new test methods as well, which reduce the amount of helium that's required. So just other facilities, so obviously electron microscopes and optical microscopes, but looking at fibers themselves. So there's some close-ups of niobium, titanium samples that you can see the sort of structures that were shown previously in real, as visualised on the microscope there. Finally, then a bit of a history of where the testing at Durham has gone. So it's really built up over the last sort of 4 or 5 years. So in 2011, they got the contract to do the witness testing of the toroidal superconductor materials, the niobium tin. And then just this year, in March 2015, that's where the second contract came along for the niobium titanium material as well. So all of the European material built, we said, for reactor will be tested after it. So that is the team there, finally. So David is the guy grinning third from the right there, so he should have been here giving the talk today, but as I say, he's attending the other meeting. Lots of information on the net there about what we do, but essentially, as I say, the Durham element of the contribution to ITER is to focus on the superconductors, measuring their performance and really improving superconductor technology in ways to try and get the same performance at ITER, which is okay. Thank you very much.